The EMBRAER 170 and 190 uses three independent hydraulic systems to power the primary and secondary flight controls: the landing gear, the brakes, the nose wheel steering, and the thrust reversers. All three hydraulic systems use phosphate ester hydraulic fluid type 4 or 5 and operate at a nominal supply pressure of 3000 psig. System 1 and 2 are powered by an engine-driven pump, EDP, and backed up by an AC motor-driven pump, ACMP. The ACMP is used during takeoff and landing and powers the system in the event of an engine or EDP failure. A power transfer unit is installed between the two systems to transfer hydraulic power from System 1 to System 2 without mixing fluid between the systems. This is used for landing gear retraction and extension in the event of an engine or EDP failure. System 3 is powered by an AC motor-driven pump and uses an additional ACMP as a backup. The hydraulic control panel, located in the cockpit overhead panel, allows the crew to manually control the firewall shutoff valves, the AC motor-driven pumps, and the power transfer unit for all three hydraulic systems. During normal operation, the ACMPs and the PTU are controlled automatically when the respective rotary switch is selected to auto. An exception is the ACMP3A, which can only be manually controlled to either on or off. When in auto mode, the ACMP will automatically start when the following conditions are true. ACMP 1B and 2B will start when the flaps are selected to any position unequal to flaps 0. ACMP 1B and 2B will also turn on automatically in case the EDP of the respective side fails. ACMP 3B will be turned on if ACMP 3A is not operational. ACMPs will not come on if speed is below 50 knots regardless of flap position. The PTU will start to operate if EDP 2A fails during takeoff or landing. The hydraulic system is designed in such a way that even a failure of two hydraulic systems will not result in a complete loss of flight-critical functions. The following hydraulic users are powered by Hydraulic System 1, installed in the left center fuselage bay. Left outboard elevator PCU. Ground spoiler pair 2. Multifunction spoiler pairs 3 and 4, left thrust reverser, outboard brakes, emergency parking brake, and the upper rudder PCU. System 2, located in the right center fuselage bay, powers the left and right inboard aileron PCUs. Left and right inboard elevator PCUs, multifunction spoiler pair 5, ground spoiler pair 1, landing gear, nose wheel steering, inboard brakes, emergency parking brake, right thrust reverser. Hydraulic System 3, installed in the aft fuselage, supplies the left and right outboard aileron PCUs, right outboard elevator PCU, and the lower rudder PCU. The hydraulic system of the EMBRAER E190-195 has a 15% greater volume as compared to the EMBRAER E170-175. Therefore, the EDPs on the 190-195 have a rated output flow of 82.9 liters per minute, 21.9 gallons per minute, at 5,568 RPM, whereas the EDPs on the 170-175 have a rated output flow of 71.92 liters per minute, 19 gallons per minute, at 4,825 RPM. On the 190-195, the storage volume of the number 2 reservoir is 14.75 liters, 900 cubic inches, as compared to the 170-175, where the storage volume of the number 2 hydraulic system reservoir is 12.3 liters, 750 cubic inches. Each of the 3 independent hydraulic systems include the necessary components for supplying clean, pressure-regulated oil to the hydraulic users. A bootstrap reservoir in each system provides pump inlet pressure and accommodates the oil volume change in the system. Contaminants are removed from the oil through filters in the pump discharge and case drain lines, and in the main system return line. The flow of pump case drain oil through a hydraulic fluid-to-fuel heat exchanger for systems 1 and 2 is designed to prevent temperature extremes. System 3 relies only on radiation and convection for dissipating heat. Each of the 3 hydraulic system reservoirs are of the bootstrap type, using system high-pressure fluid acting on a piston to supply pressurized fluid to the pumps. The storage volume of the number 1 hydraulic system reservoir is 12.3 liters, 750 cubic inches, and for the number 2 hydraulic system reservoir, 14.75 liters, 900 cubic inches. While the reservoir for System 3 has a minimum capacity of 6.15 liters. The reservoirs contain a quantity indicator, measuring the remaining fluid volume in the reservoir. A dial gauge, visible to ground personnel, indicates fluid quantity in the reservoir. This information is also displayed in the cockpit on the MFD hydraulic system synoptic page. In the event of low fluid quantity, a message will be displayed on the ICUS for the respective system. A temperature transducer monitors hydraulic fluid temperature in the reservoir and displays the information on the hydraulic system synoptic page. The 2 engine-driven pumps, EDP, are variable delivery hydraulic engine-driven pumps mounted to the engine gearbox. Pressurized hydraulic fluid is supplied to the EDP via the suction line. The pump provides hydraulic pressure to hydraulic systems 1 and 2 whenever the respective engine is running. It supplies the desired system pressure by varying the volume of fluid output to the system, depending on system flow demand. The pump produces a rate discharge pressure of 3,000 psig and has a rated output flow of 64.4 liters per minute. The ACMP is also a pressure-compensated type, similar to the EDP, but is driven by an electric AC motor. Pump operation can be automatic or manual, using the respective rotary switch in the cockpit. The ACMPs on systems 1 and 2 are powered by the electrical AC bus, normally supplied by the generator installed on the opposite side, ensuring the function of each system in case of engine failure. On hydraulic system 3, the ACMP 3B is powered by the AC bus 2, and the ACMP 3A is powered by the AC essential bus. which can also be powered by the ram air turbine. The firewall shutoff valves are powered as follows. The EDP1 firewall shutoff valve receives power from the hot battery bus 1, and the EDP2 firewall shutoff valve receives power from the hot battery bus 2. All three filter manifold assemblies incorporate a bypass valve in the return circuit to permit bypassing of hydraulic fluid in the event of excessive restriction of flow through the filter element. A variety of pressure transducers and pressure switches installed on the filter manifold are used for system monitoring and control. The pressure transducers, one for each system, are connected to the MAU and provide hydraulic system pressure indication to the cockpit crew. On the MFD hydraulic system synoptic page, pressure values are displayed in amber for values below 1800 psi, green for values between 1800 and 3300 psi, and white for values above 3300 psi. Two pressure switches located on the filter manifold assembly monitor pressure output from the two pumps and are used to enunciate hydraulic pump and hydraulic system failures. Systems 1 and 2 each have a fluid-to-fuel type heat exchanger to provide cooling of the hydraulic fluid. The source of the fluid is the combined case drain flow for both the EDP and the ACMP, which passes through the heat exchanger and returns to the system reservoir. The cooling medium is the aircraft fuel in the collector tanks. A bypass valve is installed to improve the hydraulic system warm-up response time after a coal soak by diverting the flow of the fluid around the heat exchanger. Hydraulic fluid power can be transferred from System 1 to System 2 without sharing fluid between the two systems by means of a power transfer unit, PTU, installed between the two systems. With the rotary switch in the auto position, the PTU will operate in the event of a loss of the right-hand engine or right-hand EDP to provide hydraulic power for landing gear retraction during takeoff and landing. Firewall shutoff valves are located in the EDP suction line for Systems 1 and 2. Overheat protection is performed by temperature switches installed in System 1 and 2. They will cause automatic closing of the relevant firewall shutoff valve in the event hydraulic fluid temperature reaches 125 degrees Celsius, 257 degrees Fahrenheit. Once a switch is tripped, the firewall shutoff valve will close and stay closed. System 3 has a temperature switch installed that will cause ACMP 3A and 3B to switch off automatically in the event hydraulic fluid temperature reaches 125 degrees Celsius, 257 degrees Fahrenheit. Nitrogen gas pre-charged accumulators installed in all three systems provide bootstrap pressure to keep reservoir pressure at a sufficient level for pump startup and to prevent pump cavitation. In conjunction with the priority valves, the accumulators are designed to maintain bootstrap pressure for overnight parking of the aircraft or for pump start at high altitudes following a failure. The System 3 accumulator also has the important function of providing flow to the flight-critical hydraulic users during dual-engine failure until the ram air turbine generator becomes operational, which then powers the ACMP 3A via the AC Essential bus. The accumulators also function as pressure dampers during rapid movements of hydraulic users. Control of the hydraulic system is performed using the hydraulic control panel, located in the cockpit overhead panel. The 4 AC motor-driven pumps, ACMPs, and the power transfer unit, PTU, can be selected by the flight crew using rotary-style control switches, whereas the firewall shutoff valve is controlled by a guarded push-type switch. ACMPs 1B, 2B, 3B, and the PTU use 3-position double-pole switches, while ACMP 3A uses a double-position switch. Each backup ACMP has its own rotary switch that can put the ACMP or PTU into auto control, off or on. In auto mode, ACMPs 1B and 2B turn on automatically during takeoff and landing, or when primary pump pressure is lost. ACMP 3B only activates in auto mode when ACMP 3A is lost and does not activate during takeoff and landing. Similarly, the PTU in auto mode turns on when EDP-2A fails during takeoff and landing. Since ACMP-3A is the primary power source on System 3 and is always on, its rotary switch has only 2 positions, on or off. The automatic control logic for ACMPs 1B, 2B, 3B, and the PTU is implemented in the SPDAs. Note that there is no automatic logic associated with ACMP 3A. It is either on or off. In case the respective SPDA goes offline, these pumps can be manually selected on. This is accomplished using a direct hardwire connection provided from the cockpit switches to the integrated control circuits of each hydraulic pump. The ACMPs 1B, 2B, and 3B will be in automatic mode control when their respective cockpit switch is placed in the auto position. With electrical power available, they will automatically be started when the following conditions are true. ACMPs 1B and 2B will be turned on when flaps are at 0 degrees. ACMP 1B will be turned on when EDP-1A is not operational. ACMP 2B will be turned on when EDP-2A is not operational. ACMP 3B will be turned on when ACMP 3A is not operational. To prevent overloading the electrical generator during single generator operation whilst ACMP 3A is running, and to prevent ACMP 1B and 2B from being started simultaneously when the flaps are selected to 0 degrees, a staggered 1.5 second time delay is incorporated between the start of ACMPs 1B and 2B. In addition, start inhibits for ACMPs 1B and 2B are used to minimize the hazards to ground crews during normal aircraft maintenance activities. Manual mode control is accomplished by the flight crew placing the respective ACMP cockpit control switch into either the on or off position. The ACMPs will be turned off when the ACMP cockpit switch is in neither the on or auto position. Whenever the ACMP cockpit switch is placed into the on position, that ACMP will be commanded on regardless of the state of the auto mode control logic. Note that ACMP 3A can only be controlled manually. No auto mode exists. The firewall shutoff valves can be controlled either by the fire handles located on the overhead panel or by the engine pump shutoff push switches located on the hydraulic system control panel. Operating one of the two firewall shutoff switches will provide electrical power to the shutoff valve motor, and the valve will close, shutting off hydraulic flow. In case of an engine flameout in flight, a depressurization control is required to depressurize the EDP, to reduce the residual drag on the engine, and to facilitate relighting of the relevant engine. The control logic is implemented within the left and right FADECs, and the depressurization solenoids are controlled directly by the MAUs. The main components of the hydraulic system are two variable delivery engine-driven hydraulic pumps, two firewall shutoff valves, two hydraulic fluid to fuel heat exchangers, four AC motor pumps, one hydraulic power transfer unit, one PTU selector valve, three hydraulic filter manifolds, five case drain filters, three hydraulic system reservoirs, three accumulator assemblies, three accumulator pressure gauge fill points, Systems 1 and 2 each contain a variable delivery hydraulic engine-driven pump, EDP, which provide the primary source of hydraulic power. Each EDP is flange-mounted to the engine gearbox with a V-band clamp and is driven through a splined input shaft. The discharge, suction, and case drain ports of the pump are connected directly to the aircraft hydraulic system through hoses, which incorporate quick disconnects at the aircraft end of the hose. The case drain port is located on the top side of the pump, near the mounting flange, a position designed to maximize case drain cooling of pump components. An electrical connector provides control to the solenoid valve that reduces discharge pressure and input torque required during engine windmill relights. The engine-driven pump is a pressure-compensated type, varying the volume of fluid delivered in order to maintain the desired system pressure. Pump displacement of the EDP is controlled by means of a compensator valve and stroking piston arrangement. The compensator valve performs an integration by metering a volume of fluid to the stroking piston, proportional to the change in pump output. The stroking piston in turn controls the angle of the hanger subassembly, which determines the amount of fluid expelled during each stroke of the pistons. An increase in system flow demand causes the pump discharge pressure to decrease, reducing the force applied on the compensator spool. The compensator spool shifts to the left as the compensator spring force overcomes the force generated by the discharge pressure acting over the spool diametral area. When the discharge pressure decreases to a value defined by the setting of the spring, the spool uncovers a port in the sleeve, allowing oil to transfer from behind the stroking piston to the case. The rate piston extends due to the force from its springs, which drives the pump hanger to a larger angle as the stroking piston retracts. This results in greater flow output from the pump to meet the system flow demand. The EDP incorporates a two-position, three-way solenoid valve to reduce the discharge pressure and input torque required during engine windmill relights. Valve activation is controlled by the FADEC to reduce discharge pressure to approximately 1000 psig 68.9 bar, whenever the aircraft engine N2 is below 15% and no weight on wheels. With the depressurization valve de-energized, the engine-driven pump operates as a normal pressure-compensated variable displacement piston pump. When the depressurization valve is energized, the solenoid valve position shifts, resulting in pump discharge pressure being ported directly behind the auxiliary stroking piston, bypassing the compensator. With sufficient pressure applied across the auxiliary stroking piston area, the auxiliary piston pushes on the primary stroking piston, decreasing the hanger angle and reducing the pump outlet flow. Since the compensator is bypassed, the pump discharge pressure is reduced to the minimum pressure required to destroke the unit. When the applied voltage to the solenoid is removed, the de-energized solenoid valve returns to the normally closed position, venting the pressure applied behind the stroking piston back to the case. Discharge pressure is blocked at the solenoid valve, and normal pump operation via the compensator resumes. Systems 1 and 2 each contain a firewall shutoff valve, located in the EDP suction line outside the engine pylon area. In the event of an engine fire, this valve can be closed to stop hydraulic fluid from reaching the engine. Each assembly consists of a DC motor-operated ball-type shutoff valve with a visual position indicator, a thermal relief valve, a relay, and 4 switches. The thermal relief valve is built into the assembly to provide protection from downstream overpressurization due to thermal expansion when the shutoff valve is in the closed position. A double-pole, double-throw relay is used to control the direction of motor rotation. When a valve close command is manually initiated by the pilot, the 2 relay switches move to the opposite pole, and motor rotation begins in a direction to close the valve. The 2 motor control microswitches are actuated by cams as the valve ball rotates and are used to limit the motor rotation. When the valve reaches the end of its travel, one of the switches opens to interrupt current to the motor. The 2 position indicator microswitches are actuated by cams as the valve ball rotates through its 90 degrees. They are used to indicate valve position to the data acquisition unit. Systems 1 and 2 each have a hydraulic fluid-to-fuel heat exchanger to provide cooling of the hydraulic fluid by using the aircraft's fuel supply as a heat sink. The heat exchanger consists of a series of looped aluminum alloy tubes, mounted to a flange that includes the inlet and outlet connections. A bypass valve is installed between the heat exchanger inlet and outlet lines on both Systems 1 and 2 to provide the hydraulic system warm-up response time after a cold soak. The valve controls the flow of pump case drain fluid to the heat exchanger as a function of fluid temperature by diverting fluid flow around the heat exchanger at low temperature. In addition, the valve provides a pressure relief function to allow fluid to bypass the heat exchanger if its pressure drop becomes excessive. The AC motor-driven hydraulic pump, ACMP, is an axial piston type unit. It has a cylinder barrel containing 9 pistons, which are driven by an 115 200-volt AC 400 Hz electric motor. Operation of the AC motor-driven hydraulic pump is similar to the operation of the engine-driven hydraulic pump. The rated output of the pump is 3.0 gallons per minute, 11.3 liters per minute, at 2850 psig, 197 bar minimum. This rating applies with an inlet pressure of 50 psig, 3.4 bar, when the motor is supplied with three-phase, 115 200-volt AC, 400 Hz electrical power. The Power Transfer Unit, PTU, is a fixed displacement unidirectional device used to transfer fluid power from System 1 to System 2 without sharing fluid between systems. The PTU will operate only if there is a loss of the right-hand engine or right-hand EDP to provide hydraulic power during landing gear retraction and during descent and landing, unless manually selected on. The Power Transfer Unit is a unidirectional device consisting of two fixed displacement axial piston rotating groups housed separately and connected by a drive shaft. The motor side is slightly larger in displacement than the pump side to account for mechanical losses within the unit while maintaining system pressure. The pump and motor sides include case drain ports to route internal leakage and idle bypass flow back to the reservoir. The idle bypass flow permits the PTU to operate smoothly and continuously at all demand flows from zero to rated flow. System 1 utilizes a solenoid-operated valve to control operation of the Power Transfer Unit motor. The PTU selector valve is a three-way, two-position, pilot-operated spool valve. The valve is normally closed and pressure-operated to the open position. The valve is designed to operate normally at 3,000 psi, 207 bar, and will withstand transients up to 3,750 psi, 259 bar. When the PTU select valve is energized, pilot pressure and spring force act to move the main control spool to its open position, admitting system pressure to the valve outlet port. With 3,000 psi, 207 bar, 100 degrees Fahrenheit, 38 degrees Celsius, fluid applied at the inlet, the valve will allow a minimum flow of 10.0 gallons per minute, 37.9 liters per minute. In this condition, the pressure drop across the valve is 60 psid, 4.14 bar, or less. Upon removal of pilot pressure, a spring moves the spool to the blocked position, porting cylinder pressure to return. The hydraulic systems 1, 2, and 3 each contain a filter manifold assembly to provide filtration control in the hydraulic system. System 1 and 2 assemblies filter the supply fluid coming from the aircraft pumps, EDP and ACMP, the return fluid from the users, the reservoir fill fluid, and incoming supply pressure fluid from the ground service panel. System 3 filters the supply fluid coming from the aircraft pumps ACMP 3A and 3B, return fluid from the users, reservoir fill, and incoming supply pressure fluid from the ground service panel. The assemblies are comprised of the following: the filter elements and bowls, the differential pressure indicators, DPI, the bypass relief valve, the check valves, the pressure relief valve, the pressure switches, and the pressure transducer. Hydraulic fluid pressure and return flows are routed through identical separate 5-micron filters. The EDP case drain flow is routed through a 15-micron filter. Identical pressure and return filter elements were used to reduce the number of sizes of filter elements required to maintain the aircraft. The filter manifold assembly contains an automatic shut-off device for each filter location to prevent fluid drainage when the filter element is removed. The shutoff head is spring-loaded to the closed position and is normally held open by the top of the filter element. As the filter bowl is removed, the shutoff head will descend and close off the opening of the filter bowl housing. Should a filter bowl be installed without an element in place, the shutoff head will only partially open, causing sufficient pressure drop to operate the relevant differential pressure indicator. Although the pressure and return filter elements are interchangeable, the filter bowls are not. They are designed for their specific operating pressures in order to minimize the weight of the filter manifold. Different thread sizes prevent wrong installation of the pressure and return filter bowls. Each filter bowl is secured with a ratchet-type retention device. Each filter manifold assembly contains a resettable differential pressure indicator for each filter element, 3 total, to show when filter element replacement is required. This is a non-electrical device that gives a visual warning by raising a red indicator when the differential pressure across the filter element rises to 70 plus or minus 10 psid, 4.83 plus or minus 0.69 bar. Once actuated, the red indicator remains extended until reset manually. The indicator is designed not to actuate when the fluid temperature is below 50 degrees Fahrenheit, 10 degrees Celsius, and it incorporates a time delay to prevent inadvertent actuation due to momentary flow surges. A strain gauge type pressure transducer is located on each filter manifold assembly to monitor system pressure. It generates a voltage signal proportional to the applied pressure, and the transducer contains its own electronics to amplify the output of the strain gauge to a level acceptable to the data acquisition unit. 2 pressure switches located on each filter manifold assembly monitor the pressure output from the 2 pumps connected to each manifold. A separate pressure switch monitors the operation of the PTU. There are 4 case drain filter manifolds in the hydraulic system, 1 located in each of systems 1 and 2, and 2 located in system 3 to provide filtration from all ACMPs. The case drain filter is comprised of the following: the filter element and bowl, the automatic shutoff device, the differential pressure indicator, which extends in case of filter blockage, and a check valve. Each of the 3 hydraulic systems contains a reservoir for storage of hydraulic fluid. The assembly is a bootstrap type, utilizing system high-pressure fluid acting on a piston to provide the following functions: supply fluid to the system or accept fluid from the system when the total volume of fluid in the system changes. Provide sufficient static pressure to deliver fluid to the pump at the required flow rate and above the pump critical inlet pressure. Collect air for manual removal with a bleed relief valve. The reservoir provides the necessary fluid volume demanded by the hydraulic system, including pressurization of the pump inlet. Changes in fluid volume due to thermal expansion and contraction, system leakage, and differential area of the user actuators have been taken into account in sizing the volume of each reservoir. The major components of the reservoir assembly are low-pressure storage chamber, bootstrap cylinder, bleed relief valve, suction shutoff valve, quantity indicator, and temperature transducer. Each hydraulic system contains a separated piston type accumulator pre-charged with dry nitrogen gas. The accumulators provide bootstrap pressure, which keeps reservoir pressure at a sufficient level to assure startup of the system pumps and prevent cavitation. In conjunction with the priority valve, the accumulators are designed to maintain bootstrap pressure after the following conditions: overnight parking of the aircraft, failure requiring pump start at high altitudes. In addition, the System 3 accumulator provides a very critical role during dual engine failure by providing flow to the primary hydraulic users during the time interval required to establish ram air turbine generator operation. The system accumulators are also intended to augment the pumps during periods of transient flow demands and to dampen system pressure transients caused by rapid movement of hydraulic users. System 1 has an accumulator with a gas volume of 100 cubic inches, 1.64 liter. System 2 accumulator has a gas volume of 50 cubic inches, 0.82 liter, while System 3 utilizes an accumulator with a nominal gas volume of 160 cubic inches, 2.62 liter. A charging valve and gas pressure gauge are attached to the aircraft's ground service panel for accumulator servicing. The priority valve is a simple inline device containing a pressure relief valve and a check valve. The valve controls the flow of fluid as a function of inlet pressure and closes off flow when the downstream pressure falls to 2000 psig, 138 bar. Each hydraulic system includes a priority valve installed in the system bootstrap circuit to maintain positive bootstrap pressure to the system reservoir for around 10 hours after system shutdown. This provides a positive pressure on the ACMP inlet to facilitate startup of the pump. System 1 includes a priority valve upstream of the PTU motor to ensure proper system pressure is maintained before transferring power to System 2. This prevents overspeed of the PTU. System 2 includes a priority valve installed in the supply line ahead of the landing gear and steering components. This valve closes off flow to these components during periods of peak system flow demand, giving flow priority to the flight control components that are essential for flight. The normal operation of the hydraulic system is largely automatic. Very little pilot input is required. The system architecture and control philosophy is such that it can cope with most abnormal aircraft operating conditions or hydraulic system failures without requiring pilot action. As Systems 1 and 2 have engine-driven pumps as the primary pumps, the systems will pressurize with engine start. Operating the switch for ACMP 3A on the cockpit control panel starts the hydraulic system number 3 primary pump. The remaining ACMP switches and the PTU switch must all be set to auto before flight. Should a switch not be in the right position for flight, an ICAS message will be displayed, alerting the flight crew that a switch is not correctly set. Note that the hydraulic system allows for a single-engine taxi using either engine, but ACMP 2B must be operating if the left engine is used in order to provide hydraulic power to the nose wheel steering and inboard brakes. When the aircraft is ready for takeoff, ACMPs 1B and 2B will come on automatically as soon as the flaps are extended. This will result in the pumps being warm and already running should an EDP or engine failure occur during takeoff, thus minimizing the effect of switching to the backup pump. Once takeoff is complete and the aircraft has commenced to climb, the backup pumps will switch off when the flaps are stowed. The System 3 backup pump, ACMP 3B, is not switched on during this phase as there are no high flow demands on System 3 and because ACMP 3A is on the AC Essential bus. System 3 would not be affected by the loss of an engine. During the climb, cruise, and descent flight phases, the hydraulic system uses only the primary pumps to provide the power required by the flight controls. Under extreme low temperature operating conditions, a specific hydraulic system start procedure is used. This procedure will raise the hydraulic fluid temperature to its minimum operating temperature before the aircraft is ready for flight. This procedure involves running the ACMPs for a certain amount of time before engine start, and then running the ACMPs and the EDPs for some additional minutes after engine start while the engines are warming up. During this period, the PTU will also be run to ensure that all of the cold fluid is displaced from its circuits. Some cycling of the hydraulic system users is also required to ensure that cold hydraulic fluid has been displaced from their circuits. Once the warm-up procedures are complete and the hydraulic system parameters have reached their minimum operating limits, the aircraft is ready to taxi.
In the landing phase of the flight, ACMPs 1B and 2B will again automatically switch on when the flaps are extended. This is to ensure that the pumps are active and warn if an engine failure or EDP failure occurs during the landing. The backup pumps 1B and 2B will shut down with flaps at 0 degrees or 60 seconds after touchdown, whichever comes first.
Unless the hydraulic synoptic page has been selected Open, there will be no readout of the hydraulic system's operating parameters on the flight deck. If a hydraulic system failure occurs, or an external failure that affects the operation of the hydraulic system, the appropriate ICUS message will be displayed, prompting the pilot to open the hydraulic synoptic page and check the hydraulic system status. Should a primary pump failure be detected during any stage of the flight, any one of the backup pumps will switch on automatically under the control of the SPDAs. The hydraulic system's architecture and level of redundancy is such that it is able to accommodate most aircraft or hydraulic system failures without degradation to the aircraft's operation. During normal operation, the hydraulic system will operate at a temperature comfortably below the high temp caution threshold and considerably below the overheat warning threshold, the only exception being on-ground operation on an extremely hot day, where System 3 fluid temperature may reach the high temp threshold and cause the ICUS message to be displayed. Switching System 3 off while the aircraft is on the ground and switching it on again for flight operations can counteract this. An hydraulic fluid overheat condition may be caused by the failure of a pump compensator, which would cause the pump's swash plate to go to the maximum flow condition, causing the excess flow from the pump to pass through the system relief valve located in each system's filter manifold. This would result in a rapid rise in the temperature of the hydraulic fluid. The overheat threshold may be passed approximately 1 minute after the failure. In this event, the overheat protection is performed by temperature switches installed in System 1 and 2. They will cause automatic closing of the relevant firewall shutoff valve in the event hydraulic fluid temperature reaches 125 degrees Celsius, 257 degrees Fahrenheit. Once a switch is tripped, the firewall shutoff valve will close and stay closed. System 3 has a temperature switch installed that will cause ACMP 3A and 3B to switch off automatically in the event hydraulic fluid temperature reaches 125 degrees Celsius, 257 degrees Fahrenheit. The loss of a single engine would result in the loss of both the EDP and the IDG attached to that engine. This would not result in the loss of a hydraulic system, but would result in the loss of the backup pump in the system on the good engine, and the system on the side with the failed engine will be operating at a reduced flow capacity on its backup pump. Some hydraulic system monitoring and reporting functions would also be lost, but that would not prevent the hydraulic system from operating. The operation of System 3 would only be affected by the loss of a single engine if it were the right engine that was lost. In that case, the backup pump would not be available. In the case of the loss of a single engine, all hydraulically powered flight controls would remain fully functioning, and the PTU would be available for landing retraction and extension in the event of the loss of the right engine. On landing, the thrust reverser on the lost engine would be inhibited from deploying to avoid putting a high flow demand on the backup pump, which could cause the system pressure to drop. In the event of the loss of both engines, either one at a time or simultaneously, ACMP 3A will initially turn off due to the loss of the electrical power when the IDGs go offline, and the system accumulator will provide power to the flight controls on System 3 for the period while the ram air turbine deploys, spins up to operating speed, and restarts ACMP 3A. There are sufficient flight controls on System 3 to maintain control over the aircraft in all three axes and enable a controlled landing to be performed. At ram air turbine deployment, SPDA-2 commands the pump unloader valve to open, which reduces the fluid flow through ACMP-3A during pump startup. At the same time, the flow limiter valve is energized, which reduces the fluid flow to the users to 1.75 to 2 gallons per minute. This allows the ram air turbine to spin up faster to its operational speed. When the ram air turbine is spooled up and is producing power to the AC essential bus, ACMP-3A will start, and the pump unloader valve will be commanded to close, and system pressure will increase to normal pressure. The flow limiter valve will remain on as long as the ram air turbine is deployed or the ram air turbine generator is producing power. Hydraulic system operation for ground maintenance purposes is possible in two ways: by operating the ACMPs from a ground power supply, or by using the APU's IDG. Alternatively, hydraulic power can be provided to the users by a ground power supply connected to the quick disconnects on the ground service panels for each system. A safety interlock is built into the control logic for the ACMPs when they are in auto mode. The safety interlock will inhibit the ACMPs from starting automatically unless at least one aircraft generator is functioning. This allows maintenance activities to be conducted on the electrical distribution system and the flaps without the risk of the backup ACMPs inadvertently starting. Reservoir servicing consists of bleeding air and filling. Bleeding is performed by opening the bleed relief valve at the top of the reservoir and holding it open until all of the air has bled out. The valve is spring-loaded to the closed position and will close itself once it has been released. Reservoir filling is carried out from the reservoir fill point on the ground service panel for Systems 1 and 2 and inside the rear fuselage for System 3. The hydraulic system must be depressurized before reservoir filling can be accomplished. This is done by depressing and holding the button on the dump valve until the flow noise stops. The reservoir fill points are located so that the same person that is filling the reservoir can see the reservoir's quantity gauge. Placards are located adjacent to the reservoirs to define the fill range in percent for various fluid temperature ranges and for the hydraulic system conditions required for servicing. Once the reservoirs are filled, the relevant system needs to be repressurized by operating the ACMP to recharge the bootstrap circuit. The reservoir level must be checked afterwards to verify that the change in fluid volume does not exceed the allowable limit. The accumulators are charged from the accumulator fill point, also located on the ground service panel. A placard adjacent to the accumulator fill point contains instructions on charging levels and conditions. Crew alerting and hydraulic system condition indicating is achieved via the Engine Indicating and Crew Alerting System, ICAS. Various sensors are installed in the hydraulic system which provide information to the MAUs in order to display the hydraulic system performance parameters on the hydraulic synoptic page, HSP, of the multifunction displays, MFD, in the cockpit. The MAUs also use these parameters, along with other signals from other aircraft systems, to enunciate any hydraulic system problems on the ICAS display. On the interactive schematic, you will be able to view the different sensors, their locations, and their functions. The hydraulic synoptic page presents the following information to the cockpit crew on a display page dedicated to the hydraulic system. Reservoir quantity for all three systems. Fluid temperature for all three systems. System pressure for all three systems. Firewall shutoff valve, FWSOV, position. Hydraulic pump status for both EDPs and ACMPs. PTU status. Both analog and discrete data are used for the hydraulic system synoptic page. Analog data is used to display actual values, reservoir fluid temperature, quantity, and hydraulic system pressure, and pictorial gauges, reservoir quantity, and system pressure. Discrete data is used to indicate hydraulic flow paths, failed pumps, PTU availability, and firewall shutoff valve position and availability. The Engine Indicating and Crew Alerting System, ICAS, is used to draw the attention of the flight crew to the existence of any aircraft system abnormality. You can now select all warning, caution, or advisory messages for display on the ICAS. Or you can select the type of information you would like to be displayed on the MFD. By clicking on the messages on the ICAS, you will receive additional information regarding their meaning and the system logic behind the message. By clicking on the highlighted symbols on the hydraulic synoptic page,
You will receive the respective ICAS messages and the additional information regarding their meaning.